other file, and again in a way that is not static, right? And theoretically, it should work, except for one thing that I didn't think of, and that is, in fact, we need to extern it, right? Again, trivial.c, and in fact, it can be static, thinking about it, but I have to do an export symbol. Because again, we need to tell the in-kernel linker about it so it works appropriately. So you'll see here that I've actually been able to make it static, and I've called export symbol in order to make the appropriate function work. So what I'm going to do now is I'm going to, whoopsies, build it. And so I'll get out of here. I'll do a make. So the thing about externing is you only need to do externing for something where it's stored, so for a variable. Functions, we provide prototypes all the time without externing, so you don't need to extern function pointers. Now, I do unfortunately need to add this to the make file, so let's just quickly edit that, and for some reason, my editor is doing silly things. So let's do the build. Here we're doing make. And this will be the last of this because my function isn't a prototype. Yeah. I'll just get rid of the editor. So again, we're not relying on the kernel, on the compiler linker to do this, so it can be static. The fact that we are exporting it using export symbol is sufficient. It's just that the compiler itself gets messed up. So I'm making a mistake of some sort that I am not seeing. Trivial. I shouldn't have to. Isn't a prototype. No, but the thing is, you don't need to provide it in this particular case. I guess the kernel does. Well, we will try that then. I believe it. You're probably right. Yep. No. Function declaration isn't a prototype. Void foo. Okay. Sadly, we're out of time anyways. It doesn't matter. All I wanted to show you here was that, in fact, when you build the two together, this is what happens when you try to write code on camera. All I wanted to show you was that when you have modules and one depends on the other, when you insmod them out of order, you get an error. That's pretty much all I wanted to show you. Once we install them and then use modprobe, it would have automatically loaded them in the appropriate order. Okay. Anyway, that's it for today. Unfortunately, we've just run out of time, and we need to get on to the next presenter. The next talk that we were giving is on U-Boot, but otherwise, for those of you who are here to see modules and kbuild, I hope I answered your questions. I hope you know more about modules and kbuild, and I hope this now brings you into the ability to write your first kernel code. Yeah. Yeah. And we have a couple of questions. I'll take two questions, then we're going to have to move on. So.
Location of the header files for the kernel version that's installed on the
It'll be under user source by default. That's where the package puts it. No, you have to install the package first. So the package. Yeah. Yes. Yeah. Question. Yes. Nothing. We're gonna give you those on a USB stick. So there's nothing you need to do. Okay. So the next talk is momentarily.
on. 1, 2, 3, 4. And I'll make adjustments as necessary so we get a good level, okay? Thank you.
To record your talk, would you mind if I recorded your talk?
No, absolutely, do it, sure.
Can I ask you to do another favor and wear another mic?
Yeah.
Wireless mic.
I mean, it's going to be recorded
You'll
by the
sound
conference,
better.
so you can just get the recording from the conference. Yeah, it's going to be recorded.
Okay, thanks.
There we go. Okay. Yeah? Again,
All right, let's get on to the next one. Probably already tired of me speaking, but let me just introduce the next person. This is Marek. He's from Dex, I guess.
Yeah, that's right.
He's been working on U-boot for a really long time and is here today to talk about U-boot,
Yep.
specifically on the Pocket Beagle, but just generally how to do it the right way. So, introduction to U-boot, the right way.
Yeah, can you actually hear me? If I,
Oh, is it on?
it's probably not on. Well, it says on, but
It does say on, doesn't it?
yeah, let's see. Test, 1, 2, 3. Okay, so it has to be like, is this better? No? Probably still needs to. Yeah, what about now? Test, 1, 2, 3. No? Yeah, let's try this. What about, no, no. What about now? 1, 2, 3, no. Yeah, I mean, if I have it like here, then it's working, but it's like not exactly what I would like to do. Yeah, anyway, so I guess I'll be talking like that for a while. Let's get to the U-boot talk. Just like Ben said, I'm a software engineer. I work on U-boot, Linux, OpenMBDit, and this is the stuff I work on mainly. I am maintainer in those 3 projects, one way or the other. In U-boot, I do USB, I do SOG FPGA or NSS stuff. Yeah, and I'm one of the most active maintainers there. That's quickly about me. Okay. Yeah. How about this? No? So where should I? Can you just assemble it for me?
I can do that. I can do this. I'm going to put it right here. Let's see if it's and go like
Yeah. Test, 1, 2, 3. Hello. Test, test, test. 1, 2, 3. Yeah. 1, 2, 3. Does it work? Test, 1, 2, 3. Yeah, absolutely.
No, where's the where is it actually? Here. Yeah, go ahead. Let me look at it for a second. No, that's in good shape. Okay. I know what's happening. It's pointing away from you. So
Yeah.
we're gonna go like this, if you don't mind.
Yeah, just whatever.
Is that gonna work?
So how is it now? Can you hear me? 1, 2, 3. Test. 1, 2, 3. Yeah, test. 1, 2, 3. Does it work? No.
Something is wrong. I'm not sure exactly what. I'm gonna try it.
Test. 1, 2, 3. Yeah, there we go. Now it's better. Yay. Test. 1, 2, 3.
Yeah, you're good.
Yeah.
Go ahead.
Okay. Yeah. Well. Oh, yeah. This is so much better. Super. Thanks. Yeah. So I wanted to start with a slide about booting a computer. So basically, what happens when you turn on the device which you have on your desk is that there's some sort of power sequencing happening in the CPU, obviously, but then the CPU has to end up somewhere in the memory, which is called reset vector, and in that place, in memory, there has to be some initial code. Now, this will be your first stage bootloader. It's nowadays going to be in the chip because the technology has just advanced so significantly that people want to boot from something else than parallel flash. So there is some sort of bootloader buried in the chip, which does the initialization of the platform and then loads the next stage bootloader from some external media, which can be like SD card, or it can be USB, it can be whatever, something more complex. Usually this second bootloader is loaded into an on-chip RAM on the Pocket Beagle. It is the MLO. It's loaded into the on-chip RAM, executes it, and that again does some initialization of the platform. It usually brings up the DRAM up, and then loads the U-boot proper into the DRAM, executes U-boot in the DRAM, and after that, U-boot loads the Linux kernel into the DRAM, executes the Linux kernel, and the Linux kernel does its thing again. So this is basically the multi-stage loading which happens today on a contemporary platform. It didn't have to be, it wasn't like that every time back in the past, it usually happened to be that the CPU core had the address bus directly routed to the pads of the chip, and you just attached a parallel flash, and the CPU core just directly booted from the parallel flash. So your first code running on the core was something you controlled. Nowadays, it's not like so. So the first replaceable code on the Pocket Beagle is U-boot, and I would like to talk about this today. So U-boot is a bootloader. Yeah, that's the one thing it does. It can load the next stage and execute it, which usually is Linux. It can be anything else. It can be BSD, whatever, doesn't matter. But it can also be used as a really good debug tool and boot monitor. That means, like, the U-boot can start the Linux kernel, right, and then you will not see it again, but it can also drop into U-boot shell, where you can, like, poke registers, operate buses, and so on, debug your platform, which is really useful not only if you're, like, trying out new hardware, but also when you have, like, your platform, for example, out of manufacturing, you want to check out quickly if things work or not. And I would like to show you how to use that U-boot shell and really, like, how to poke the hardware and really test out everything. So, first of all, this is how U-boot looks like. If you power up a system, what you see here is the U-boot SPL. That's the U-boot preloader, and that just loads the U-boot proper from the, in this case, SD card into DRAM after initializing it, and then it starts the U-boot proper. The way you can identify that these things started is by them just printing out on the serial console that they are running. This print, this U-boot SPL and U-boot information is like the first thing U-boot prints out on the serial console to notify you that, hey, I'm running, like, at this point, everything still worked. What else do you see here? U-boot itself, U-boot proper will print which CPU it is running on, how much DRAM you have. It will also print the board name, which is somewhere down here. Right. In case you're getting or trying to get support from the U-boot community, you should include definitely the U-boot version. In case you have some extra patches, you should include that information as well, that you have some extra patches. You should definitely include which board you are using. Now, once you get through the entire U-boot boot log, you will get to the auto-boot countdown. So U-boot will be running this countdown. If it reaches 0, it will just do the default boot action. If you interrupt the boot countdown, it will drop into the U-boot shell. Minor note on the U-boot SPL versus U-boot. There are 3 different things actually which you can build out of the U-boot sources. Nowadays, you will usually meet only the U-boot SPL and the U-boot proper. And what that means is that with modern platforms, you just, the first thing that happens or that can be loaded is some sort of small piece of code, like tens of kilobytes big, which has to initialize DRAM. So U-boot caters for that and is able to build like a stripped down version of U-boot, which will do the DRAM initialization and then chain load the U-boot proper. This is what the U-boot SPL is. There is also possibility to build even smaller version of U-boot, which is the U-boot TPL. You will likely never run into that, but just so you know it exists. It usually is present on devices which have like Samsung One NAND, and we are talking about like units of kilobytes big artifact built from U-boot sources, which basically is responsible for loading like the U-boot SPL into the on-chip RAM, executing that, and then the U-boot SPL is responsible for initializing the DRAM, loading U-boot proper into the DRAM, and executing U-boot proper. So on some specific devices, you may also have to use the U-boot TPL, but usually you're never going to run into that one. So that's it for the introduction into U-boot. Now I would like to show you some commands which are useful in U-boot. First useful command is echo, which just allows you to print whatever, some string. It doesn't interpret any control sequences The other thing is help command. This is really useful because even if you get like completely alien platform, which you have no idea about what it can do, if it runs U-boot, if you get into the U-boot shell, you can just do help. It will print you all the commands that the U-boot supports, so you'll know what you can do with that U-boot. Now, you can also do like help command, which will give you more detailed information on that command. And this is useful even if you are like confident with U-boot, but you just don't remember what's the order of like arguments for specific command. You can just do like help command and get this information. In this case, it's like help for the USB subsystem, which you can see in here. So what can we do? We can stop the USB, we can reset the USB bus, stop it, we can get a USB 3 listing, we can get USB test mode running, that sort of stuff. So you can get like a detailed help. If you need further help, you can look into the U-boot documentation, which is in the U-boot sources. You can see it down below here. Also, in case you have some specific question, you can visit the U-boot IRC. Right? It's on Freenode, hash U-boot. I mean, if you ask questions, please wait at least like a while. Don't just immediately leave because no one responded to your question quickly. The people maybe like in Europe, just ask at the time when they are asleep. Okay, they just cannot reply immediately. And if no one really replies on the IRC, which usually doesn't happen, but it can, just ask in the U-boot mailing list. So, that's it for getting help. Now, getting for board info, even if you have like a board which you know about, but just want to check what the board is about, is done using the bdinfo command. In here, the interesting parts are the DRAM information here. So basically, U-boot is using just physical addresses, right? And in case you need some sort of memory with which you can operate on the U-boot shell, you just run bdinfo, look at the memory layout, you see, okay, there is a DRAM, it starts at 8,000 on this board. What is that? Yeah, here it starts at 8,000, it's 2,000 with 8 zeros big, and this is the area which you can use for whatever you want, loading files, experimentation, whatever. It has just a small detail that U-boot itself will relocate itself at the end of the DRAM, so you should probably avoid like the last 16 or so megabytes of DRAM, because otherwise you can corrupt the U-boot or its structures, and then bad things will happen. The system will become either unstable or it will hang or something like that. So like using most of the RAM is okay, it's just the last couple of megabytes which are not okay. You can also see at what location U-boot itself actually relocated. It's the relog address somewhere down here. I actually have to look it up. Yeah, the relog address, that's the relocation address at which U-boot placed its code. But this does not take into account the malloc area, which is like above that, and U-boot stack, which is also above the malloc area. So you should like round it up a little and then avoid that piece of memory. I mean, you have plenty. You have like 512 megs of memory anyways. So there's some other interesting stuff in here. Ethernet address, which is like the current Ethernet address. We can't really make use of that on the Pocket Beagle, but in case you have a board which has actual Ethernet, then yeah, the current Ethernet address is also in this listing. All right. So now that you know what your memory layout looks like, you can also do something with the memory, like read it, write it. For that, we have the memory dump and memory write commands, MW and MD. They allow you to access both DRAM and device registers. And since device registers can be sensitive to access with, they also support suffixes, which allow you to select like how wide the access to the register should be. We support byte. What else do we have here? word access, which is 16-bit long. That's the default. That's the 32-bit, and quad on 64-bit platforms, which is 64-bit access. By default, the MD, the memory dump, will read 64 words of data, but you can specify how much data you actually want to read out from the memory as an argument to the MD. Another trick is that if you do like MD and some address, potentially some amount of data, and then print enter, it will dump that much data. If you press enter one more time, it will dump one more time that many data again. So like you can do like MD some address, okay, but I want to read some more, enter, it will read some more, and so on. This way you can keep dumping the memory. You can actually see it at the end here. So this is just a matter of pressing enter here. Okay. You can also use these commands to access device registers. In this example here, I'm using it to toggle the blue LEDs on the Pocket Beagle board. So what I do is, first I just dump registers of the GPIO controller. This is something I fished out of the datasheet for the OMAP chip. So I know that at address 4804C130 there is GPIO controller direction registers, then there is input register, then there is output register and value register, something like that. So I set the direction register here to, most of them are inputs, those which are set to 0 are outputs, that's the 4 LEDs, and then I can set the output value register using the MW command to just turn on the LEDs. You can just try it on the Pocket Beagle yourself. You will see that the blue LEDs come up. Now, this particular masks I'm using here are converted to like these bit masks here, and just these 4 specific bits which are connected to the same GPIOs which control the LEDs on the Pocket Beagle. All right. Now, there are a couple of additional commands which allow you to poke around with memory, which are not that well known and are less used. It's memory modify. This command, if you run it on some sort of address, will read out the value on that address and print it on the command line and ask you which value you want to store to that address. So if you supply a value, it will store it to that address. If you just press enter, it will do nothing and automatically increment the address. If you supply a minus, then it will go like one address before. So this might be interesting if you want to like interactively operate with some sort of register or something. Also, nm is another command which doesn't do the automatic increment of the address. So you can basically do something like nm 0x4804 C13C. This will allow you to change the GPIO controller output register, and then you can just specify different values and toggle different LEDs on or off. With that? But this stuff? This is just syntax highlighting which went wrong. Sorry about that. It's probably just shell syntax highlighting. Yeah, but this example is just showing that you can do the nm on some sort of address. It will read out that address. You can specify something. If you don't specify any value here, it will just skip the address, not write anything in there. And this is basically the LED example done using the memory modify command. Yeah. Oh, and if you specify Q, then you can just exit from the command. Okay. Last 2 commands which are kind of useful. CP is memory copy. The same thing applies as on the memory dump and memory write. And CMP is memory compare. Now, this is useful if you're debugging stuff like you're reading data through some sort of bus, and you want to be sure that when you read the data twice, that the data are exactly the same. For that, you can use the CMP command. In case the data are the same, the CMP command will tell you so. In case they are different, the CMP command will tell you that there is this sort of offset, and at that offset, the data are different. So, okay, these are the tools for manipulating the memory and checking the memory. But what I would like to look at next is the U-boot shell. So U-boot actually, so U-boot actually has two types of shell which you might run into. Nowadays, by default, it should be the hash shell, which is like much more modern, much more sensible shell. But there used to be a shell version before that in U-boot, and it was really painful to use that. So you might have run into this, and the experience was probably not so pleasant. Hopefully, hopefully nowadays you'll just run into the hash, which is imported from BusyBox some time ago. But anyways, if it's a pain in the, then you're running the old one. Pretty much. You will notice severe limitations of the shell if you like try to do something. What's that? If it doesn't behave like a born shell, then you're likely running the old one. There was quite a simple test in that. Let's see. Yeah, for example, I believe tab completion didn't work on the previous one, so you can try that one, for example. Anyway, we'll focus on the hash shell because this is what's enabled on the Beagle as well, anyways, and I would like to talk about that one. It's similar to what you are used to with your Bourne shell on your regular PC, and also it does support environment. It does support environment persistency. You can have scripts in the environment in addition to values. So that's what the U-boot shell does. Now, the U-boot environment is pretty much what you know from your standard shell. That is key value storage, but there are a couple of details to it. First of all, the default environment, so the default key values are stored in the U-boot binary. That's the default environment. But on most of the boards, there will be some sort of dedicated U-boot environment storage, so that when you save the U-boot environment, it will be stored in this additional environment storage. And when you power cycle the board, whatever you had in your environment, if you saved that, it will not get lost, but it will get loaded from this storage. Now, U-boot always has a live copy of the environment, which is in the RAM. But unless you explicitly save it into the storage, it will get lost. So you can kind of change the live copy of the U-boot environment, do whatever you want with it. If you reset the board, then all those changes will be lost, unless you explicitly store it. So you can experiment with the U-boot environment, whatever you want you can do to it, and then just reset the board, and you will start from fresh, which is probably convenient at this point. Now, to operate the U-boot environment, there are a couple of commands for that. Printenv to print the environment content. If you just run it like so, without any arguments, it will dump the entire environment. On the Pocket Beagle, the environment is quite rich, so if you run like printenv, it will be just a really, really long list. You can also just say, okay, printenv specific environment variable, and it will just print that one. For example, printenv arc will print ARM because ARC is ARM. There might be a bit of a confusion about printenv and envprint. So the situation is as such. Recently, we decided to consolidate everything under the env command. So you should be using like env print, env save, env whatever. This is the modern way to do it. Obviously, for compatibility's sake, and because you will see it everywhere on the internet, there are legacy aliases like printenv, saveenv, setenv, and so on. So that's just to clarify the situation. Okay, now you can print the environment. Great. You can also access the environment as variables. So if you do like echo $arc, like you see at the bottom, it will also print arm. So whatever is in the environment, whatever keys are in the environment, you can access them this way as variables. Now, if you want to modify the environment, you can use setenv, just setenv, name of the variable, and then the content, or envset. That's an alias for that. You can also do like treaty questions if you want to poll the user for some information using askenv, and you can also, if you have some sort of like long script in the environment, you just use the edit env, and you can kind of move left and right in that script, tweak it. Then when you hit enter, this environment variable will be adjusted. So you can use those. And finally, if you did some changes to your environment, you want to make them persistent, you can use safeenv. This will just commit it into the environment storage. Now, in case you want to undo that stuff, like you want to just get back to the default environment, you can use just like env default-a. This will reset the local copy of the environment. If you want to make this persistent, then you can do like env default-a and then follow it by safeenv. So that's the environment access. Yeah. There is not. No. Yeah, you would probably have to do that yourself on the remote machine side. So. No, there is not. No. Well, patches are welcome. Yeah, okay. So anyway, that's it pretty much for all the environment variables. You can also use the run command to store scripts in the environment. So if you have like environment variable which you set to like echo hello, and then you do run name of the other environment variable, it will run it as a script. So in this case, if you do like run foo, it will print hello because that content of the environment variable is just evaluated as a script. You can also chain multiple of these commands using the semicolon operator. That's just like you know it from the shell. Just like you know it from the shell, it just ignores the return value of the previous command, so it will just run those commands one after the other. So in this case, hello world, it will print hello world. That's the run command. But yeah, there's one pain point here, which is the U-boot environment variables. People keep running into this one. If you do like, if you want to set some sort of script in the U-boot environment which is accessing variables, it just so happens that you will run into this first case where the line 2 is immediately evaluated, and then you wonder, okay, well, why is it printing like something which I do not want? Yeah, because it is immediately evaluated. This that foo variable there. Now, to work around it, the best way to do it is just to use the single quotes around the entire script content when you're setting it into the U-boot variable, just like it is done here at the end. So that's probably the best practice around it. I mean, yes, you can escape the $sign, but then if you like start chaining the command, you'll also have to start escaping the semicolons and all the other $signs. So when you have like a more complex script, it gets a little difficult. Using the single quotes around the entire script is just so much easier. So there is that. Another thing is U-boot has a couple of variables which have special meaning. Var will always contain the version of the U-boot bootloader. So if you want to inquire, for example, your customer, okay, which version of U-boot are you running? You can just tell them, okay, either run the var command or do like printenv var, and you will immediately get the latest information, which version he's running. If you have multiple like standard input-output possibilities, you can configure those using the std in, std out, std error variables. If you set that variable, it is immediately triggering the change in the input-output, so be careful about that. Interesting variable is load address. So if you're loading any sort of data from anywhere, this will be the default load address to which U-boot will load those data. I'll get to loading commands in a bit. Now, once the loading is done, U-boot will set the file size variable, and that will be the amount of data that U-boot loaded. So, like if you load, for example, a file from SDMMC and want to print it, you can do like MD whatever dollar file size, and it will print exactly the amount of bytes that was loaded. So this is the automatic variable, which is useful, really useful. It is also useful if you want to like write to a flash storage when you downloaded some file from, let's say, TFTP, and you want to write the exact amount of bytes, then you can just use the file size. Let's see. Yeah, boot command is the default boot command. So in case you have this auto boot countdown in U-boot when you just start it up, if the countdown counts to 0, it will run this boot command, which is the default command which is executed then, and it's usually meant to start the Linux kernel. Boot args, Linux kernel boot arguments. Interesting variable is pre-boot. Now this will be useful, for example, if you do some sort of commissioning. This is a script which is executed before the U-boot, auto boot even kicks in. So in case you have something which needs to be done at that point, you can put it into the pre-boot environment. And it can be useful if you have it like built into your default environment, and then in the pre-boot, you do your like one-time thing, for example, one-time provisioning of the board, and then set on pre-boot to clear it from the environment, and then save env to write the environment into the system. So the next time when the system reboots, there will be no pre-boot variable, and it will just not do this sort of provisioning action anymore. Then there are a couple of variables which are used to configure network IP address netmask, server IP, ETH header for MAC addresses. And finally, there's one last command which I would like to show you about for manipulating the environment, which is setexpr. This might not be present on all the systems, but it's really like an environment manipulation, like Swiss Army knife sort of device. So this one allows you to it allows you to do like basically three things. One is load memory content into U-boot variables. Another thing which it allows you to do is do arithmetic operations, both on U-boot variables and on memory addresses, which can be useful like if you're doing, for example, loops which need to pull some sort of bits somewhere in memory or whatever. Yeah, you know, you can do like plus minus, that's the standard multiplication, division, and you can do also bitwise operations, which is useful. And in case you have regex support enabled in U-boot, then they also allow you to do basic regular expressions. So you can like have a variable in the U-boot environment and apply basic substitution on it, for example, including like back references and this sort of stuff. It's all there. So that's what you can do with an environment. But with the U-boot shell, you can also do conditional stuff. Basic things like true false commands return 0 for true, and false returns non-zero. It also has a return value, so we can have U-boot check for that. And we also support the $question mark variable, which prints the return value of the previous command. We also do support the shell if conditional, where you can provide whatever if command, then do some operation, else do some other operation that's supported. This one, We also support the shorthands for conditional expressions with the or and. This is also supported. Here is some example of that. So if true, echo hello will print hello, obviously. So there's that. We support test command, so we can like use the standard shell test command, which allows you to do like arithmetic comparison and string comparison. This is all supported as well. You can use it within the if command. So like if test something something, then do something. This is supported. There is one small detail about that, is we do not support if negation. That means like if not something, then do something is not supported. But what you can do is like if something, then do true, else do whatever your desired operation is. Right. We support for loops, iteration over lists of elements. That's just like you know it from the Bourne shell. For loop, while loop is also supported. This example here will run indefinitely, so you can like press Control C to abort this while loop, this one. And that's it pretty much for the U-boot shell. There are also hardware manipulation commands. Here is a gpio command, which you can use to manipulate the GPIO pins on your board. We support reading out the GPIO input, which, by the way, also has a return value. So you can do like if GPIO inputs some number of the GPIO, then do some action. This is also possible. You can set the GPIO, you can clear the GPIO, you can toggle GPIOs using this command. So if you need to poke GPIOs in the U-boot environment, you can just do that. I2C command for accessing the I2C bus. On the Pocket Beagle, you have actually multiple I2C buses. If you do like I2C bus, you'll see the list. You will have 3 of them. And you can use the I2C command to operate the devices on those buses. I2C dev allows you to select which bus you want to access. You can access only one at a time, so you have to always like switch with I2C dev, and then you can do something like I2C MV to write memory or MD to dump memory. Convenient is I2C probe. It allows you to like probe the bus for devices which are sitting on the I2C bus. One thing about the I2C probe is that it can confuse some old I2C devices. So I2C by default is not bus which you can probe. Nowadays it works mostly, but there can be some devices which will just be confused by this like probe action, so be careful about using this one. Yeah, and I2C speed, you can set up the I2C speed. In this example here, I'm accessing the accelerometer actually on the Bacon Bits Cape. So I'm setting I2C bus to 2 because the accelerometer is on bus 2. And then I do I2C probe. Yeah, I see there is just one device, the accelerometer. Okay, I can just read the registers using the I2C MW. I specify that it's supposed to be chip 1C because that's the I2C address of the accelerometer. And I'm reading from 0, 8 bytes. And this is what I get out of it. Yay, success. I did manage to read some data out of it. Okay, so that's for hardware poking commands. Next thing, loading from storage. So you can access different kinds of storage, SATA, SDMMC, NAND, whatever. For each of that, we have a dedicated command to access the raw storage and its common properties. But you can also load from file system if you have the file system on like SATA, SDMMC, USB sticks, whatever. So you can, for that, you can use the load command or ls command to list that storage device. There used to be times before this generic file system interface was available where we did have dedicated command for like listing XFS, listing vFATFS. So you might might run into U-boot which will have like these commands, xls, explode, this sort of stuff. But nowadays, the modern way to do it is just with ls and load the generic interface which detects the file system. Here's an example of loading file from SDMMC. So what I do here is first, there's a lot of extra stuff, but first I rescan the MMC so that I have like all the latest information from the controller. Then I'm looking at the partition table. I see that I have only one partition in here, which is of type Linux. Okay, there is probably X file system on that. I can list the MMC. In this case, it's controller 0, partition 1. Okay, I see that there is some sort of file. Oh, it's perfect. I can load the file to load address, which is the default load address. I'm just specifying it there. And then I can dump the content of the file, and I'm using the file size here because U-boot conveniently set that up for me to just exactly dump the amount of bytes that the file has. We won't be able to exercise this one, loading from network, but U-boot has a network stack in it. It's UDP only, it doesn't support TCP. But this is not that limiting, and it significantly reduces size. So this allows us to use ICMP, obviously, ARP, and then we can use TFTP. We can use NFS over UDP. We can use DHCP to obtain information from the network. Now, in order to use the U-boot network stack, you need to set up a couple of properties. Obviously, you need to configure your network. In case your vendor does not provide you with any way to obtain MAC address, you might need to set that one up as well. And then you can start just using ping to test whether the network connectivity works. You can TFTP download files from your TFTP server, or you can just use DHCP to obtain the IP address information and then download the files. So that's how loading from network works. Now, if everything else fails and you just have no way to get files into the U-boot, you can still use load yes, which allows you to load files over serial line. So the way this works is U-boot supports multiple of these protocols, actually. We support X-modem, YES modem, and Kermit. And in this example, I'm using the YE modem. So you just do like load YE. You can specify also an address here to which you want to load the stuff. And then in your terminal emulator, you just say, okay, send over Y modem this file, and U-boot will be receiving the file and storing it to that address. So you can do that. It is useful in case your Ethernet, for example, doesn't work for some reason and you still want to, yeah?
Is the X-modem the CRC version?
That I don't know, honestly. But I can just look it up if you want.
That's okay.
Okay, but that's a valid question, actually. I would like to look it up. Thanks. Yeah. So you can just load stuff over serial, and I would like you to actually try this one out. Now, finally, it's a bootloader, right? So you probably want to boot the kernel, but even this is not that easy because if we have like gazillion different Linux kernel formats, on ARM you will find that image, which is the raw one. This is basically the Linux kernel image with a decompressor squashed together. You just put it into the RAM and basically set up a couple of registers, just jump to it, and the Linux kernel starts loading. There is no protection against bit rot. Now, in the times of old, there was an attempt to solve this problem, and the U image came up, which is like the U-boot image, but it's been legacy since forever because it's like just an envelope for a file. So there is a CRC32, and there are a couple of metadata in that U image, which say like where that image should be loaded, what's the entry point, and a couple of information about that image. But the CRC32 is just today, it's too weak, it's useless. So this has been legacy. But there has been a image format which supersedes that, and that's the FIT image, which is like a multi-component device tree-based image format. basically allows you to write some sort of device tree specification and pull in blobs like the Linux kernel, the device tree blob, and that have configurations which say, okay, this kernel goes together with this device tree, and U-boot will know how to interpret that and boot the kernel, including the device tree, and so on. And you can bundle any amount of blobs. You can configure different checksum algorithms and so on. So this sort of flexibility is what the fit image is all about. In case you're building some sort of embedded device, definitely look at the fit image because this is what you want to deliver in the field. Now, booting the kernel, it really depends on which image format you have, that you use different commands for that. So for Z images, we use bootz. For U images and fit images, we use bootm. You just specify like the image address. In case of the bootz, you might need to specify also device tree location if your machine is device tree capable. And you can specify also initrd address. There we go. On ARM64, you have boot E because for some reason bootz was not good enough, so we have to use that one. And here's an example of booting the kernel. So first of all, we need to set some boot args because otherwise the kernel would not know where to send the serial out path. Then we just load the VM Linux, we load the device tree, and then use bootz somewhere around here to start the kernel with the device tree address, and then the kernel starts booting. So it's that easy to boot a kernel on the Beagle. Now, speaking of device tree, U-boot is able to also manipulate the device tree using the device tree command. So when you load the device tree from your storage into the RAM, you can say FDT adder pointed to that address of the FDT in RAM, and then you can modify the FDT in RAM. In case you want to modify it, you need to first do FDT ray size, because whatever you just loaded into the RAM is like the flattened device tree blob, and there is no extra space. So if you want to add nodes, you first need to do like FDT resize to have U-boot just add some extra space for your new nodes. Once you do that, you can do like FDT print to print whatever is in the device tree. You can do FDT set to add new nodes into the device tree, and all that is like done on that device tree blob which you loaded into RAM. So if you then do like bootz with a Linux kernel and that blob, the Linux kernel will be given this modified device tree blob. So if you want to like experiment with tweaking the device tree, here is your way to do it. Yeah. Yeah, so what you can do is like you load your device tree into the RAM in U-boot, then you use this FDT command to like point U-boot, hey, here is a device tree. And now the FDT command will be able to tweak the device tree, or like add new stuff to it, remove stuff from it. What's that? Yeah, you have to load the device tree manually into RAM. So the way like booting the Linux kernel with device tree works is that you load the kernel into RAM, you load the device tree into RAM, and then you say, assuming that it's a Z image, right? Then you say, okay, so jump here, but with these registers, with these ARM core registers, which point to here in the RAM where the device tree is sitting. And the kernel will boot, it will start executing, and the first couple of instructions in the kernel just say, okay, if these registers are set to these specific values, then this kernel is being booted with device tree capable bootloader, and the device tree is telling me, hey, the bootloader is telling me, like the kernel, that the device tree is somewhere in RAM, and I should use that address for the device tree location. So yeah, you have to do it explicitly yourself, like load everything into the RAM and then say boot Linux device tree. Yeah, the bootloader is passing some sort of register settings to the kernel, and the kernel is interpreting those early on in the boot. It could also be that the bootloader will pass A tags to the kernel, at which point the kernel is likely not running with device tree. So this is what happened like in the old times when ARM was being used without device tree. Yeah. Here's an example of the fit image contents. So this is like the device tree describing the fit image. Where you can see here is the kernel blob being pulled into the kernel section. You can specify a lot of properties here: name, where the kernel should be loaded, what's the entry point of it. Here I use a hash algorithm for this kernel section, which is like CRC32, but I can have like secure hash algorithm 1, 256, whatever. I can also have like this section digitally signed to prevent tampering. Here is an FDT section which is pulling in a device tree. It's an ARM device tree with, again, CRC32. And then there is configuration section ultimately here, which is tying together this kernel and the device tree. Again, it can have a different checksum algorithm. It doesn't in this example. Now, if I have this sort of fit image source file, I can compile it with mkimage. It will generate the blob, which I can then boot M on the machine. And the blob will contain the kernel image, the device tree. And you will know where to put those and where to start those. So the final bit is getting the U-boot sources. You can get them from the Git repo here. In case you need some specific tweak from a maintainer, you're in touch with a maintainer, he might point you to one of these forks, which are the maintainer trees. Both of that is available through both Git and HTTPS protocol. In case you were trying to clone U-boot sources recently, it could be that you had some trouble because we just replaced the server. So I think last week the server had some sort of failure, and it could be that you were not able to get easy access to these repos. That should now be fixed. There are also sources for the U-boot available on that USB stick you have. Now, if you want to build the sources, clone them, export the architecture for which you are building. In this case, this would be ARM. Export your cross-compiler prefix, which will be like ARM Linux or ARM known, whatever. And then make your board defconfig and make the board defconfig. In this case, it's going to be like AM335X Pocket Beagle defconfig. You can check if the defconfig is present in the configs directory. So it has to be there, otherwise you wouldn't be able to configure the U-boot. And then just make it. It will generate the U-boot binaries. That is for the Pocket Beagle, that's U-boot IMG, and the MLO, which is the SPL. And that's it for the intro part. Do you have any questions? This might have been a little bit too much. Yeah. Yeah. Oh yeah, you do like safe and this will write it into the storage. So there is this environment, storage, partition, whatever, depends on how your board is set up, into which the environment will be stored. And this will be persistent at that point. So if you do safenv, it will be made persistent, all of it, the local snapshot of the environment. Yep. Any other questions? Yeah. Yeah.
Is there a way to skip the check for the serial console at the auto boot?
What's that?
Is there a way to skip the check for the serial console at the auto boot?
If you can disable the auto boot, you mean?
Yeah, how do you always do that? If you set to 0, it still checks for
It will still check, yeah. I usually set it to like really long value when I do development, but I do not think you can disable it from the U-boot shell. You have to do it you have to tweak the U-boot itself. There should be some configuration option for that, yeah, to disable auto boot. But I would have to look it up what that is. I'd try setting boot delay to -1 maybe. That might actually work.
Okay, so what we're going to do now is we're going to take a quick break. Okay,
Yeah.
everybody back in less than 10 minutes. Then we're going to do the lab, and Marek, you
absolutely. So there's a practical part.
We're going to play with that after the break. So everybody, quick bio break, and when we come back, we'll do the practice part on the board. Incidentally,
Okay. Okay, so I think we should do the practical part. So you can play around with the U-boot a little. Does everyone have the what? Does everyone have their Beagle accessible? So what's that? Yeah, I'll help you with that. Okay. BN? BN. 1 second. Just give me a second.
Okay.
Can you help to get?
People who left didn't have boards.
Hmm?
The people who left didn't have boards.
Yeah, there's a question about Windows.
We'll sort it out. Yeah.
Thanks.
Don't worry. You're doing great. You're doing great.
Yeah. So someone will help you out in a bit. I think there.
This gentleman?
Yeah.
Okay, be right there.
Yeah. Yeah, okay, so task 0 is just drop into the serial port, get into the U-boot shell, see if you can do like stuff like version or help. If you can access that, super, that's task 0. I'll give you like a couple of minutes for that. So if you're getting bored, let me know. The slides are organized like so that, whoa, okay. Okay, I think that might be better to. All right. So anyway, before you like start discussing stuff and so on, the slides are organized like so that there is always like some sort of task here which you should do, and then on the next slide there is a solution for that. Okay. So task 1 is just to drop into the U-boot prompt. Task 2 is to like conveniently load content into your U-boot environment using the load y command. Please try it out, and this way you can kind of develop your U-boot scripts and then load y them into the U-boot environment. So you will have always like a sort of local copy of whatever you created for the U-boot. So that will be task 1. It's really like 0 and 1 are nothing exciting. Do you all have actually access to these latest slides? Okay, if you don't have access to them, they are on the EAL GitHub repo. So please download the latest slides. In case you get bored, you can start moving forward with the subsequent tasks. And if you have like a problem with task 0 or task 1, raise your hand and let me know if you need assistance. Yeah, what's that? Yeah, so you can just create your text file which contains like key equals some sort of value, key equals some sort of, yeah, exactly. Just save it as a text file and then use the load EA to load it into the U-boot and then import that file. Yeah. Actually, if you look into the slides, like a couple of slides before that, you will just find an example of it. So you can kind of put it together and it should be easy. And on the next slide, there's also an example. Yeah, EL, yeah. In the GitHub, there is latest slide. Loading environment over serial port into U-boot.
Loading the environment?
Yeah.
Just like keying them in?
Hmm?
Key,
Yeah.
set in.
No, just using loading. Just load the file.
Oh, loading the file.
Yeah, over serial ports, and then env import that content into your U-boot environment.
Okay.
So you can have like your custom scripts written on your PC, and then just import them into the U-boot environment.
Ah, very good.
Yeah.
Okay.
Conveniently. Yeah. For this.
Yeah.
That's the instruction.
Oh, that's
Yeah. Okay. So who of you actually is in the U-boot shell right now? Can you raise your hand? Okay. So what about the rest of you? Or do you have some problems with that, or do you need some assistance? Yeah. Just get there. Yeah.
Rest space, that's about it.
What's that?
I've connected both the USBs.
Yeah, but you're now in the Linux, right? So if you reboot, then eventually you'll get like this, this sort of output. This is what you will get, right? So then just press space, and this will drop you into the U-boot shell. I think you,
Sudo reboot and then that should help.
yeah, or you can just press the reset button on the board. There is like one in the middle. One of these three buttons.
And then press space.
Yeah. Just try all three of them. Something happened. Yeah, there you go. Super. Yeah. Okay. So I figured I should explain task 1 a little bit more. So the idea here is that you use the load E command to load some sort of file containing environment and import it into your U-boot environment so that you can conveniently this way import U-boot scripts. Yeah.
Or more? Because it just goes up?
Yeah, no, there is not, but you can like use shift page up, shift page down, I think. I think so. Should work. Doesn't? Maybe it's the terminal emulator property.
Okay.
What are you using for a terminal emulator?
Screen.
What was that? Can you help up with screen?
Screen?
Yeah, going up and down.
Can you,
There's like Alt, Escape,
Control B?
something like that. Try it.
That's T mark. I'm the T mark.
I think it was like Control A, Escape, like Escape, and then you can go page up, page down. Oh, is it? Okay.
And then arrow. I don't know how you get out of that mode. I use T mark, so I'm not used to the screen.
Oh? Did something happen?
Maybe I'll
Maybe you two can kind of cooperate and figure it out.
Your eyes aren't that good, huh? Press the magic key.
Yep.
Record it and slow it down. Alright, now it's in copy mode and you can scroll.
Oh,
Yeah.
that's the
Get out
one.
of that, it looks like you hit Control C to get out of that mode. Yep. Get out of it. Cool. Thank you. Control A.
Nice. So,
How is
yeah.
the first one going to be? Pretty easy? Hard?
So, here's the question. Did you manage to get this Lodi working with the Y modem? At all? Yeah. So the question is, what are we supposed to do with this task? So, what I would like you to do is prepare a text file which contains the U-boot environment. That means like a key and a value tuples in that text file. Then use Lodi to load that into memory, and then env import to import that U-boot environment. this is what I would like you to do here in this one. What's that? I don't have an example text file, but you can create one with like hello equals world. That's this sort of, yeah, exactly. Yeah, and you can probably also put some sort of script there, like, you know, foo equals echo bar, something like that. Yeah, this is kind of how it should look like. So if this is readable, you can just create a random file, then use load-e and send it over to iModem. When you finish loading, you can just do md.b load address file size. You'll see that the file was loaded, and then use envimport to import this environment file. So this is what I would like you to try, this sort of thing. What's that? What's that? Yeah, in the Linux command line, you just like use the cat command, which means read from standard input until you type EOF. So,
How do you drop into Linux?
do you have a Linux machine?
I do.
Yeah, then just run new shell in your Linux machine.
Well, I'm running U shell already on the Beagle.
Oh, no, I mean on your development machine.